today I'd like to talk about some of our recent research on active and transfer learning with partially Bayesian neural nets. So the paper just came out in Digital Discovery. The name of the paper is pretty much the same, except that there is also for materials and chemicals part, but feel free to Google it. And okay, so before we talk about Bayesian neural nets and partially Bayesian neural nets, let's just briefly revisit the concept of active learning in the context of physical sciences as well as autonomous experimentation. So whenever someone comes to me and asks if they can do machine learning for their system, the first question I ask them is, can they clearly identify a specific target or specific set of targets that they are after in their experiments or simulations? So it can be something like trying to achieve a specific phase of a material, or maybe they're after some specific property like electrical conductivity in the thin films or specific magnetic behavior. Or maybe it's something more trivial as enhancing operational efficiency of the instruments or the beamline, like number of samples they can measure per day or something like that. Or perhaps they're running simulations and they're trying to compute a set of properties over a large space of various possible compositions and structures. But anyways, and you might be surprised, but people don't always have a very clear idea of what their target may be. In fact, I remember when I was doing my PhD, well, my target was just to prepare some sample and then look at it in a microscope and see what is interesting there, right? But I never thought about identifying a specific target that I am after in my experiments. I was just looking at what is interesting and then seeing something interesting, interpreting it, and publishing papers on it. Okay, so once you identify the target of your experiments and simulations, the next question I ask is, so what is it that you can actually control in your system that can influence the target, right? So it could be something like materials growth or synthesis parameters, things like partial gas pressures, pressure in your growth chamber, right? Or starting concentrations of different reagents and type of those reagents, temperature, and so on, right? Or again, if you're after operational efficiency of your instruments, maybe these are some instrument control parameters or whatever you can control on your beamlines. Or if you're doing this in computational space, that perhaps you have a very large space of possible compositions and structures, and you want to try, and you have some generator perhaps of those structures, and you can control parameters of those generators. But also it may be just go one by one over all those structures. But in any case, the assumption here is, so I call them control knobs, but the assumption here is that there is some functional relationship between these control parameters and the target property of interest, right? This is really what we're after, and this is really what material science is all about, right? Finding this structure property relationships. And so there is some relationship, but we don't know it. Because if we only knew this relationship, we would not need machine learning. We would just have a very nice mathematical equation into which we can plug in different values of the parameters, and it will output us the exact value of the target of interest, right? So then we would not need machine learning. The reason we use machine learning is that most of the time we have no idea, or we have very little idea about this relationship, right? And so we try to approximate this relationship with a with a machine learning model, which can be a neural network, but it can be something else. It can be a random forest model, Gaussian process, and so on. Okay, that's the idea. This is pretty much what at least classical machine learning is about in physical sciences. Okay, So in the context of active learning, we want this machine learning model to be probabilistic, such that at each step, and we will define what we mean by step a bit later, but it has to output a predicted target property as well as associated uncertainty for all possible combination of our control parameters, right? Or to be more specific, for all combinations of the control parameters that we have not tried yet, right? And the reason for that is that there is this assumption that we make that our measurements or simulations are too computationally expensive to try all possible combinations of control parameters or simulate all possible structures and compositions of our materials. And because of that, we want to be smart. We want to be smart about how to select the next combination of parameters that we want to try, right? So ideally, we want to, well, if we are just exploring, we want to reconstruct this the behavior of our property of interest in this entire parameter space as quickly as possible with as few measurements as possible. If you're doing some sort of an optimization, we want to find minima or maxima of our property of interest as quickly as possible as well, without trying every single combination of the parameters. And so, okay, so the key here is to have a robust probabilistic machine learning model that can predict that property of interest for every combination of parameters, and also provide a reliable uncertainty estimate. So once we have that prediction and we have associated uncertainty, there are quite a few off-the-shelf tools, decision functions that we can use to derive the next set of parameters using these predictive mean and uncertainty values, right? In my experience, the key part is really getting reliable uncertainty estimates. Once you get them, you can just use some off-the-shelf tools to derive the next measurement point, right? So finding or identifying or building a robust probabilistic machine learning model is really the key here in my experience. Okay, so again, in my experience, this is before, maybe this will be a bit sort of biased opinion. So I personally focus on this for surrogate modeling, with Gaussian processes, deep kernel learning, Bayesian neural networks, and partially Bayesian neural networks that I'm going to talk about, right? And they tend to cover, again, in my experience, all possible scenarios in both experiments and simulations in the context of active learning, right? So Gaussian process is really the most popular probabilistic surrogate model for active learning. And by the way, I should point out that when I say, let's see if I can go back. Okay, but so when I say active learning, I kind of also mean Bayesian optimization, right? Because sometimes people say, well, active learning is just when you're the pure exploration, right? You're just guided by uncertainty, and Bayesian optimization is when you try to find maxima or minima of your target. But the overall workflow is just the same, right? So the difference is the policy, right? So how do you connect the prediction of a probabilistic machine learning model with the derivation of the next set of parameters to explore? But it can be something just as simple as your acquisition function can be prediction time plus beta times uncertainty, and then you just remove the prediction part and you just look at that uncertainty, right? And that so that's how you switch from Bayesian optimization to active learning and vice versa. So anyway, when I say active learning, I also mean Bayesian optimization, which so could be a bit confusing, so I wanted to clarify that. Anyway, so the most common surrogate model for active learning Bayesian optimization is Gaussian process, which is great. I have quite a few papers on Gaussian process applications in autonomous experimentation as well as modeling. And it's great because it provides mathematically grounded uncertainty estimates. The limitation is that it tends to work well with relatively small and relatively low dimensional data sets. And there is also this assumption that your functions is smooth over your parameter space, right? Which doesn't always hold true in real physical world. All right. So another popular tool which I've been using quite a lot in the past is called deep kernel learning, which is a combination of a neural network and a Gaussian process. So a neural network projects your potentially high dimensional data into low dimensional latent space where standard Gaussian process kernel operates. And so this helps you dealing with dimensionality aspect, as well as potentially any non-stationary behaviors that you have in your data. So the challenge here usually is that once you go from relatively simple neural networks to more complex ones, what happens is that you have this conflicting optimization dynamics between your neural network and your Gaussian process parts of your workflow. And this sometimes leads to chaining instabilities, collapse in feature space, and does not deliver the expected results, right? But it works very well for simple neural networks. Okay, and so now Bayesian neural networks. The biggest advantage, in my opinion, of Bayesian neural nets is flexible architectural design. So because there are so many different neural network types for handling different types of data out there, that if you have a simple way to turn them into Bayesian, and you kind of do because you replace deterministic ways with probability distributions, then you can apply all those different types of neural nets for a variety of for variety of problems and different data types and so on. So this is really a huge advantage. And again, there is no this conflicting optimization dynamics between different parts because there is no Gaussian process. It's just a neural net. All right, and partially Bayesian neural net we'll be talking about sort of balances computational cost and uncertainty estimation by placing probability distributions only over or a subset of parameters, right? So I made an app actually. It's the first time I made an app for sort of guiding the selection of the probabilistic surrogate model, where you can input things like your input dimensionality, latency tolerance, meaning how fast do you need to get a result, because these things matter, for example, in the context of autonomous experimentation. And then if you know something about the smoothness of your target property within your parameter space, it can also be helpful. And then it recommends a model from this for different types of models. Anyway, so let's quickly revisit what Bayesian neural networks are about. By the way, are there any questions? Because I need to drink. I want to drink water. So if there are any questions, feel free to ask.
Not for now, I believe. Just for anyone in the chat. There's like the regular chat, and there's also the Q&A. You can write them both, and I'll do it out loud.
Okay, great. Yeah, and just feel free to interrupt me because it's still like 7 a.m. here, so I would appreciate any interruption and interruptions, sort of interactive discussions. Otherwise, I may fall asleep accidentally. Okay. Anyway, so let's quickly revisit what Bayesian neural networks are. So again, the concept is very simple and it's been around for quite a while. You just replace your constant weights with the probability distribution, and that's how you switch from still early morning. To switch from deterministic neural net to Bayesian neural net, what you do is that you replace constant weights with probability distributions, right? And so this is the first step, really. You define probability distributions from which you sample your weights, and most of the time people just use a standard normal distribution. So it's zero-centered distribution with a standard deviation of 1, right? So all weights are sampled usually from that distribution. Then, because you sort of assume that there is some observational noise in the system, which is common thing to do in Bayesian modeling, so you also want to define a prior probability distribution for that noise, and then you construct the likelihood, which in this case is shown for regression model, but you can also derive one for classification and so on, right? So this is just a very standard way to define a probabilistic model, right? And the next step is you run advanced sampling techniques like Hamiltonian Monte Carlo, no U-turn sampler, or some approximate variational inference techniques to infer the posterior distributions of your probabilistic model parameters, right? So there are existing off-the-shelf tools that do it quite well. There are open source packages with those sampling and variational inference techniques. So once you have your model, you can just utilize those. And now that so basically the step 2 is training, right? Although in the world of Bayesian model, it's called inference, which causes a lot of confusion because in traditional deep learning, inference is what you do at the test time, and while here inference is actually training your model. So anyways, once you have the posterior distributions of your parameters, you can now compute predictive mean and uncertainty for any new inputs, right? So that's the general, that's the overall idea. And just few simple examples. Again, if you're familiar with this field, you've seen this a lot before. If not, let's just quickly go over it. So this is a very standard off-the-shelf skleon classification, binary classification data set, and we ask a Bayesian neural network to classify each point in this two-dimensional space and then draw a decision boundary. And this is a low noise regime, so you could perhaps accomplish the same thing with a standard neural net, except that here you also get some measure of uncertainty. But now let's go to the higher noise regime where we have a lot of mislabeled examples, and then you ask your Bayesian neural net to create the decision boundary. And the key here is that, it also provides an uncertainty estimate, and now you can see that the uncertainty is much higher on the right side, where we have far more mislabeled samples than on the left side, where we just have a few, like here's only one mislabeled sample, right? So this is pretty useful because you don't only get an answer, but you also get an idea of how confident your model is in that answer, right? Which I think this is actually a pretty good illustration. You can also use it for, and we are mostly using it for regression problems. So they are they come in very handy for problems where you have non-stationarities and discontinuities in your data, which is quite common in physical sciences data. And at least off-the-shelf Gaussian processes don't really work very well for that type of data, where you have, for example, sudden transitions between relatively smooth behavior and some oscillatory behaviors, and fully Bayesian neural networks handle that type of data quite well. Or maybe you have some phase diagram with a discontinuous transition and or set of transitions. And again, Gaussian processes don't really work very well here, but fully Bayesian neural networks work quite spectacular, right? Another very interesting application, which people don't always think of, is when you have input dependent noise, right? Because a lot of these tools, when people use these tools, they kind of assume that the noise is constant across the entire parameter space, but it's frequently not the case, right? In experiments, there are regime where it's just so difficult to measure something that you will just in certain parts of your parameter space that because you get this very high observational noise, and can we account for that? Can we incorporate that somehow into our model? And this is not really the focus of today's talk, but I feel that this is important to mention, right? That we always assume input independent noise for which we use the homoscedastic Bayesian neural nets, but we can also move to the heteroscedastic regime that allows us modeling input dependent noise. And one particular interesting idea here that we've explored some time ago is, can we incorporate, if we have some idea of how our noise behaves, how noise behaves in our parameter space, can we incorporate that model into our probabilistic Bayesian neural network framework, right? And it turns out that yes, we can. And so let's say you have something like this where your noise changes as a step function, right? But you don't know exactly where the transition happens. So what you can do is you actually can learn that noise model, the parameters of that noise model simultaneously with the parameters of your neural net, right? And then when you make a prediction, it actually tells you predicted target values, the associated uncertainty for those predictions, and also it predicts noise, and it outputs uncertainty estimates for the predicted noise. So I think it's pretty cool. Anyway, okay.
One question.
Yeah. Yes. Yeah.
So you would have to duplicate the model, like create the same model, but for the noise.
No. So there are two ways. One is you don't have any model of noise, and so what you have is that you create just this two-headed Bayesian neural net, which predicts function value and noise value, and it basically learns both from the data. So that's one approach. The second one is that you incorporate your noise model into your Bayesian neural network probabilistic framework, the one that I showed here, right? So we sample weights, and then we also sample noise from some probability distribution. So here we sample, so here noise comes from whatever physical model we have, right? And then we have probability, we put prior probability distributions over the parameters of that model, right? But then this is still the same. Then we run sampling on this entire probabilistic model, right? So we infer the parameters of our noise model and the BNN weights simultaneously, right? So we don't run anything twice, right? So it's still one run. It's just instead of sampling noise from a single prior distribution, here instead we have some model which can be something like A plus BX, right? And then A and B are sampled from some prior probability distributions, and we learn the A and B parameters together with the weight parameters. Does that make sense?
Yep, clear. Thanks.
Okay. Yeah, so this is cool, and I think people don't always take advantage of this possibility. So I something to think about, I think, because especially in experimental sciences, you sometimes just have an idea, okay, this is noisy regime, or this is not noisy, and this already can be very helpful for modeling. Okay, so then the question, yeah,
just one question.
Yes, yes, perfect. I love questions. Is there?
Okay, just gonna ask a question. You can unmute yourself now.
Yeah, okay, yeah. Hi, thank you. So I have one question regarding when you say like training on neural networks with experimental data. So how many points you are assuming at the starting?
Well, it depends on how many control parameters, aka input dimensions, you have, right? Okay. So there is, because it's all about complexity. It's all about the complexity of your function, of your target function within the within your parameter space, right? If it is super smooth, some simple monotonic behavior, you can probably, and it's like, I don't know, 2 or 3 dimensional parameter space, you can actually get away with probably like, I don't know, a dozen of points. All right, because your function is pretty simple. If it's something much more complex, you will probably need 100 of points or more. So it really depends. But I will show you examples on sort of standard benchmark data sets, like molecular solubility and some materials properties, where typically we can get a very nice predictions in a like the parameter space is like between 10 and 100 dimensions, and we can get pretty good predictions within a few hundred of measurements, like not even, yeah, like 200 of measurements out of thousands. So I don't know if that answers your question, but I'm trying not to, like, there is like really no way to give a single deterministic answer here, right? So my answer is very probabilistic.
Yeah.
Because it really depends on how complex your function is within the given parameter space.
Exactly, this is where I'm coming from, because like if you have very minimum number of data points to start with, then Gaussian process and these methods helps a lot. But when we are fitting a neural network as a surrogate model, then I feel little less confident about how much these predictions are reliable. So what is your take on that? Like,
Yes.
Because experimentally, number of data will always going to be less if we are.
Oh yeah, I fully agree with it. In fact, my background is in experimental science, so I come from the experimental
lab or something.
Yeah. So I think you're cutting off a little bit, but I think I got the overall idea. I'm not sure if it's my connection or your connection, but I think I got the overall idea. And coming from the experimental background myself, I fully agree with you. And so one of the advantages of Bayesian neural nets is that they actually are more robust to overfitting compared to traditional neural nets. And so you can obtain a reliable fit in situations where traditional neural network will just overfit your data, right? So you still need more data than you would need for even traditional Gaussian process, right? Not orders of magnitude, but you still need more data. My approach to this is, my recommendation would be to explore it on some toy problems with known ground truth. Or it doesn't even have to be a toy problem. It's like, if you have some data with known ground truth, just take 2 methods, take Gaussian process, take some classical physical modeling, and some physical model, if you have one, take Bayesian neural net and see how it performs, just to get a feeling, right? Again, as I come from, I have this empirical approach, because I've seen so many times when there is kind of a nice theory that supposedly describes the limitations of each model, but then the power and limitations of each model, but then once you start applying it to real data, it just behaves unpredictably. So I would just recommend testing it on some real world data, or even sometimes synthetic data that is close enough to real world data, as long as you know the ground truth, just to get the feeling. But I would say that one of the advantages of Bayesian neural nets is that they are more robust with respect to overfitting. So even aside from the fact that they provide uncertainty estimates, they in general more robust to overfitting. So they can actually handle small data regimes relatively well.
There is another question.
Mhm.
Okay, thanks.
Yeah.
You can unmute. Yeah.
Hi, Maxim. This is really interesting work. Hopefully everybody can hear me okay. Are
I
you
can hear
able
you.
to, oh, perfect. Are you able to also bound the error when you have a noise model here? Because I feel like that's the kind of context I've seen these Bayesian neural networks used for, is kind of providing a prediction along with like a bounded error estimate.
So when you say bound error, could you clarify a bit what we're talking about? Confidence intervals here?
Yeah, something like a confidence interval for, say, if you
Yeah,
wanted to
but
predict and look
that's
at a property.
okay. Yes, that's exactly what we have. So the shaded area here is your 95% confidence interval. I call it okay. It's I call it uncertainty because that's in my opinion what it is. But the shaded area here is the 95% confidence interval for our prediction, and we also can obtain the same confidence interval for
Yes, okay.
for noise prediction. So these are the bounds that you are talking about. The shaded area here is the confidence interval or the bounds that you're talking about.
Right, okay, perfect. So you are able to bound the confidence of both the predictor model as well as the noise model kind of separately.
Yes, and this is the key, right? Because like you can predict noise from data without Bayesian neural nets, but again, the question is how reliable is that prediction? So here you also know how reliable is your prediction of noise, and of course, the more data you have, the more the better estimates you'll get.
Sure. Perfect. Thank you.
Yeah, thank you for the question. Okay, so seems like Bayesian neural networks are amazing, but you probably noticed that I only gave you simple toy examples, right? And so that's the problem with Bayesian neural nets, is that they are just too computationally expensive beyond these toy examples, right? And so the question might have posed case, if they're so great, why don't we just always use them? And the answer is that they just tend to be, the ones that produce good results tend to be too computationally expensive beyond those toy examples, okay? Yeah, and so this is when we started exploring partially Bayesian neural nets, and this is kind of a simplified schematics of deterministic fully Bayesian and partially Bayesian neural nets. Basically, in deterministic neural net, you have your weight. So weights are connections between different neurons, right? And in the deterministic neural nets, you have a single weight connection each pair of neurons. In Bayesian neural nets, you have a sort of infinite possibility of connecting those neurons for each combination, for each pair. While for partially Bayesian neural network, we select only a subset of neurons to make probabilistic and keep the rest deterministic, right? So the idea is to reduce the computational overhead while hopefully still maintaining a reliable uncertainty estimation as well as the prediction accuracy. Okay, so a simplified schematic, but I find it to be very useful to explain at a high level what partially Bayesian neural networks are. And so this is how the actual training and inference is done. So this is a two-phase process, right? And although I tried at one point to train both probabilistic and deterministic parts simultaneously, it wasn't very successful, right? So for a variety of reasons, but I realized that it's much more reliable to and efficient to do it as a two-phase process. And so in the phase one, you do a standard deterministic training where you select a neural network architecture, you train it with stochastic gradient descent the trick here is to do stochastic weight averaging at the end of each trajectory, which helps you against noisy training objectives, especially in the small data regime. Okay. Now, the next thing you do is that you select layers, a subset of layers, or in fact, it can be a subset of weights within each layer that you want to make probabilistic. And then you use these stochastically averaged weights of your deterministic neural network to initialize prior probability distributions for those selected, for that selected subset of weights. And then you run advanced sampling techniques like Hamiltonian Monte Carlo, no-neutron sampler on those weights while keeping the deterministic weights frozen. Then you derive the corresponding posterior distributions, and then you combine the deterministic and probabilistic weights to make a final prediction on test or previously unseen data, right? So this is how a typical flow through PBNN looks like. You have basically you have an alternating probabilistic and deterministic layers. For probabilistic layers, you sample weights from prescribed probability distributions, while for deterministic weight, you use a constant value that you obtain from the SGD field, right? So one thing you can think of also deterministic part as sampled from delta distribution, right? That's how you get a constant value in practice. So actually, that's what I was referring to. I kind of try to do this where you sample your deterministic weights from delta distribution while sampling probabilistic weights from kind of normal distribution, and to do this whole thing simultaneously. But it just didn't work very well. I mean, the convergence was really horrible, and so that's why I switched to this to phase regime. All right. So anyway, I will go over real world examples and some other topics soon. But I wanted to quickly switch to a notebook. And by the way, there is a NeuroBias package on GitHub. It's on my GitHub. That it's still in development, but everything I talked about today, both fully and partially Bayesian neural networks, those noise models, it's all available. It's all open source. It's all available through the NeuroBias package. I wanted to quickly go over just one simple example to show you how this works in practice. Okay, so I have, and this is a shortened version of an example notebook that is available on the NeuroBias website. Just wanted to show you how this thing works. Let me restart and start. Okay, so you just do imports, and you can pip install it. You can pip install NeuroBias. Obviously, it's already installed on my system, but I usually import it as NB. And NeuroBias is a JAX-based package, and JAX works can work directly with NumPy arrays or yeah, I mean that's one thing that I find very convenient is that all you need to know to use NeuroBias at least at the high level is how to use basic kind of operations with NumPy arrays and how to make matplotlib plot, right? You don't need to do any sort of torch or figure out how to convert between NumPy arrays and torch tensors and such, right? So that you just need to know how to operate with NumPy arrays. Anyway, let's just make some synthetic data, right? Which looks like this, right? So this is our one-dimensional synthetic data, and we want to fit it with a neural net. That's also define our test data. So the reason I call it domain is the way I think about it always is that we have some parameter space domain, and we have some measurements in that space. But what we always want to do is we want to reconstruct a behavior of our target property or target function within that overall parameter space, right? Okay, so let's just. So the first thing we can do is that we can train a deterministic neural net. so Neurobyte provides a bunch of different architectures in Flux. So you can have MLP, convolutional neural net, even have transformers there. Right? And there is an easy API to train them. So you define architecture, then there is a deterministic NN class to which you pass this architecture, you set learning rates, number of epochs, and so on. Then you train it. And obviously the training is very fast because it's a very small data set, right? And then you make a prediction with a traditional neural net, right? So, okay, there is obviously, it's very, very simple, very straightforward. But the next thing is that you now utilize the pre-trained weights to initialize prior distributions for a selected subset of neural network parameters, right? While the remaining weights are kept frozen. And then you run Hamiltonian Monte Carlo no-return sampler to obtain posterior distributions for that selected subset, and then you combine both probabilistic and deterministic components to make a prediction. Okay, so how do we select? This is the key part. How do we select probabilistic layers? Well, first of all, I have a simple utility function here that outputs layer names and specs for your entire neural network architecture. And this is a very simple architecture, right? But basically, it tells you the layer name and how many type, it's just fully connected, how many features we have for that layer. And then you can pass it in when initializing your partial BNN. So you pass your original model architecture. You can pass the pre-trained deterministic parameters, and then you pass probabilistic layer names, which in this case, let's say the first layer, and then the final output layer, which is just a single neuron because it's regression, right? And then we initialize, and then we train PBNN using no-return sampler by default here, right? And it's pretty fast. I'm running it on my Mac M2 here, and it'll probably take about 20 seconds to complete. Let's just wait. And I always try to use scikit-learn API, so it's always fit predict, no matter what goes under the hood. I find people really like it. Okay, so we trained our partial PBNN, and now we make a prediction. So it will output predictive mean and variance, aka uncertainty, and then we will plot those results. Okay, not bad. So now we went from a deterministic prediction to probabilistic prediction, and so we have also confidence intervals here, right? Which is pretty good. Now we can select a different subset of probabilistic layers, and let's say the last layer and the output layer are probabilistic now, and the rest are deterministic. And we train our partial BNN, and you can see that it's actually a bit different now, right? So, and I'll talk about it in a few minutes. That selection of how exactly we select the probabilistic subset actually matters, right? So it's like, this is a toy example. So it's different, but it's not that different when you have the first layer and the last layer, or the pre-last layer and the last layer are probabilistic. But for more complex architectures and for more complex data set, it kind of matters. But anyway, I also wanted to point out that you don't have to do this two-stage training manually, because there is a wrapper that does it all. So if you just define your architecture, you can go straight to initializing your partial PBNN with this architecture, and then it will just do the whole thing by itself. It will train a deterministic neural net, then we'll use a subset of its weights to initialize prior probability distribution. Then it will run sampling to infer the corresponding posterior distributions, and then it will make a prediction, right? So this is highly useful in the context of autonomous science in general, because you don't want to be there all the time and manually move between two different stages of training. Okay, so this is just to give you an idea of how it works. It's hopefully very intuitive and very straightforward, so feel free to try it. Okay, now let's go back to presentation. And So we tested it on a bunch of standard molecular materials data sets like freesolve, eSol, steel fatigue, thin film conductivity, and a few others, but these are the ones that I'm showing today. And our metrics was, in addition to standard mean square error, root mean square error, was negative log predicted density and coverage probabilities, which also tell us about how reliable the uncertainty predictions are. Right? And so what we did here is that we took a very simple multi-layer perceptron structure, and we really wanted to understand, so each layer had the same number of neurons, except for the last layer, which has only a single neuron. And we really want to understand what is the difference between making the first layer probabilistic versus the last layer versus intermediate layers, right? So does it even matter? And it turns out, yeah, it matters big time. So here's an example, right? So the red curve here, the red curves here are the partial BNNs with the input, with the first layer and the output layer probabilistic. And the other colors are for intermediate layers and the final layer being probabilistic. By the way, the reason I always have the output, that single neuron in regression model probabilistic, is just empirically I found that it helps with chain instability. You don't really have to include it. It will still work if you just exclude it, but practically it helps with the chain instability, so it's always there. Anyway, so you can, and we have also the fully Bayesian neural network here, right? So you can see if you made only first layer probabilistic, then the performance is actually pretty close, both in terms of prediction accuracy and uncertainty estimates to a fully Bayesian neural net. But keep in mind that for it really matters what layers we make probabilistic. And it's funny because kind of intuitively we would think that, well, just making the last layer, the last few layers probabilistic will work. But it turns out that it's much more efficient to make first layer or first two layers probabilistic, which was kind of unexpected. But I thought it was pretty cool, right? But anyway, I think the key takeaway is that so partial BNN can approach the performance of full BNN, but you need to know which layers to make probabilistic. And I think it's a very interesting area to explore beyond a simple model. And I will show you an example with a transformer neural network in the end. But anyways, but it's we see it over and over again for different materials and chemical data sets. This is fatigue strength prediction. This is based on real experimental data, which is why it's far noisier than eSol, than the molecular solubility example. But you can see the same behavior. So the red curve here again is the first layer probabilistic, and you can see that it performs better than anything else, right? Both in terms of prediction accuracy and uncertainty estimates, right? So one cool thing here is that we can also take advantage of convergent diagnostics developed for the field of Bayesian modeling to judge how well our both fully and partially Bayesian neural nets were trained, right? And so there is this R-hat value that people always use to judge the convergent diagnostics of their Bayesian models. So basically, for each parameter, you get this value for every parameter, and usually people are like, well, as long as between 1 and 1.1 is good. If it's above 1.1, probably something is not right with your model. But okay, this is great when you have like 5 or 10 parameters, but what if you have hundreds, thousands of tens of thousands of those R-hat values? You cannot really go one by one. And so we just look at the statistics, right? And we say, well, if more than 90% of those R-hat values are within the acceptable intervals, then our training was done well, right? If we see many, half of the R-hat values are above the acceptable, beyond those acceptable intervals, well, maybe we need to go back and see what went wrong. Maybe we need to adjust our prior distributions and so on. Yeah, so we also, I don't have much time to talk about it, but we did apply PBNS in the context of autonomous synthesis experiments in the reaction diffusion coupled systems, and they performed quite well. So I will skip this part. But one thing I wanted to quickly talk about is it's not even so much transfer learning. It's about how we actually initialize ways of both Bayesian and partially Bayesian neural network. And I already kind of this when I said that when we use partially Bayesian neural nets, we initialize our weights at the values of the stochastically average weights of deterministic neural nets, right? But and this sort of gave us an idea that, well, you know, when you run Bayesian neural networks, we say that we replace weights with probability distributions, but like where exactly do the parameters of those distributions come from, right? How do we choose those parameters? And in the reality is that we don't really think much of it. We just practically people just choose the normal distribution, zero-centered normal distribution with a standard deviation of 1, right? And to be fair, it works relatively well. But one thing that we sort of played with is, okay, let's say that we retrain a standard deterministic model in some computational space, and then we can use constant weights of that model. Constant is not the correct word. We can use the deterministic weights of those model, of that pre-trained model, to initialize prior probability distributions for weights of the model that will be trained in real world experimental space, right? And this is kind of, it's a very simple idea, but it turns out it works remarkably well. I call it pre-trained priors, right? Well, technically you pre-train like one parameter of that of your prior, right? It's the normal distribution. What you pre-train is the mean value of that distribution, right? And so if you do that, it actually outperforms standard zero-centered priors quite well, right? So here is an example, and where we compare standard priors and pre-trained priors, and pre-trained priors handily outperform standard priors, especially in the earlier stages of training, right? And so we can, if you do this sort of, and this is what I mean by transfer learning here, and if we do this transfer learning from theory to experiments, we can also assign what I call a degree of trust in our theory, right? Through the width of this pre-trained, through a width of this pre-trained prior. So when it's too narrow, it will be dominated by theory. And so if there is significant gap between your theory and experiment, then it actually won't learn very well from your experiment. It will still learn, but just not very efficiently. And once you start increasing the width of that prior, it will be able to balance both prior knowledge coming from theory and real world experimental data. And there is usually some sweet spot where you can have this optimal balance between utilizing theoretical knowledge and also adapting to real experimental observations, okay? And so we did it for a couple of data sets. For example, the band gap data set, where the theory data came from materials project, and the experimental data came from Mudbench experimental band gap data set. And it performed quite well again, and we see that whenever we have pre-trained priors based on the theoretical observations, the model that utilizes those pre-trained priors performs much better than just using non-informative standard priors, right? And again, this tau is an empirical parameter which controls the what I call a degree of trust in theory, right? So yeah, so this is what I think that it doesn't have to be a transfer learning from theory to experiment. It can be transfer learning between different modalities, fidelities, so different fidelities as well, right? If you have low and high fidelity, you can have a model pre-trained. You can have priors pre-trained on low fidelity data and apply it to high fidelity observations. But I think one other thing I wanted to mention here is that like I like this idea of pre-trained priors because there is, instead of constraining your model like by I don't know, introducing some additional penalty term in your loss function, what you do here is that you just give it a good starting point, right? And then you just let it explore on its own, right? And that starting point expressed through prior can be very helpful. All right. Finally, and I don't have much time left, but I talked about using simple architectures because they were really great for testing and sort of getting an understanding of both power and limitation of this approach. But we also moved to more complex architectures, including transformers. So, okay, if you can utilize this partially Bayesian concept for standard multi-layer perceptrons, we can also do it for more complex architectures, including convolutional neural nets, recurrent neural nets, and transformers. And so, for example, for transformers, we tested what's the difference between using probabilistic final layer versus making attention block probabilistic, or just having a probabilistic token embedding. And it actually kind of matters, although the results are still, I wouldn't call them conclusive at this point. What we see is that it does matter what part of transformer you make probabilistic and which part remains deterministic. But so far, when you also think in terms of a computational efficiency, I don't have this graph here, but for computational efficiency, but if you think also in terms of computational efficiency, then it seems like, again, the same idea that the first layers are more important than the last ones. So if you make your token embedding layer probabilistic, then it's actually, it provides a pretty good predictive accuracy and uncertainty estimates within a reasonable computational time than when you make final layer probabilistic or when you make attention block probabilistic. And the other thing I wanted to mention here is that when I talk about simple multi-layer perceptron, we can just take an entire layer and make it probabilistic. When you deal with something like transformer, even making a single like embedding layer probabilistic is still insanely computationally intensive. And so there is an option to make only a subset of weights in that layer probabilistic, while the remaining amounts will be deterministic. Now, how exactly you choose that subset is a very interesting question. The NeuroBias provides a couple of weights based on weight magnitude variance. It also runs some basic clustering techniques in the weight space to select those Bayesian components within each layer. But this is still something that I don't think has been explored well, and so please feel free to play with them. But yeah, again, we can basically say, well, we only want to have 100 probabilistic weights out of whatever several thousands that we have there, and then it will select those probabilistic weights and train the partially Bayesian transformer, and then you can use it to make a prediction. So again, it's all sort of there is a lot of very interesting empirical results, and there is code out there, open source, that you can go and try, right? And I think this is still a very open area of research. We see it works for simple data. We see it works for simple models. We see it works. The conclusions we derive for simple models seem to be transferable and generalizable for more complex models. But there is still so many there are still so many things to explore with respect to how exactly we select which components to make probabilistic versus which ones to keep deterministic. All right. Yeah. So this is just main takeaways. Nothing really special here. But yeah, let's just keep it. Yeah. That's all I wanted to talk about. So I hope this was useful. Forgive me bubbling at some times. It's still like not even 8 a.m. Here on the West Coast. I'm still sleepy. But I hope it is useful. Keep in mind that there is, again, an open source project called NeuroBias on GitHub that explores the concept that I've talked today about. And please feel free to contribute, or just to complain about something not working, or if you found some bug or something like that, right? There are examples there, and yeah, that's all. Thank you for your attention.
Yeah, thank you so much, Maxim. That was pretty interesting. And I guess for the sake of time, we can skip questions now, but they can reach out to you, I guess, on your email. It's on the paper, or LinkedIn.
Yep.
It's also
Let me
let me
put. Let me stop sharing quickly, and I will put the paper link in the chat.
I just pasted the archive.
Oh, thank you so much.
I saw it was like just published in the journal a few days ago.
Yep. But archive version is fine too. Yep.
Yeah.
Thank you so much.
It was great. I'll definitely reach out because I have a few questions on my side. But again, thank you so much for presenting. And yeah, we'll be uploading the recording next week.